So the next session is more now not in the view of molecular communication now. It's post-Shannon theory. It somehow will show you the next two talks how common randomness will help and how we can generate common randomness. So I think that's it's also interesting. I think for molecular communication in principle, we also had some discussion about that randomness and common randomness helps sometimes and can be increased performance. Here it's more on the viewpoint on a technical way, on an analytic way. And the first talk will be presented by Rami. He's from the Technical University of Munich. He is a PhD student at Holger Boche's group, and he just submitted his thesis, and his main topic was common randomness, so he's really an expert in that. And today he will present common randomness generation from finite compound sources. So Rami, the stage is yours.
Yes. Thank you, Christian, for the nice introduction. So the topic of my presentation will be on common randomness generation from finite compound sources. And this is a joint work with Moritz Wiese, Christian Seppe, and Professor Holger Boche. So I will start by giving an overview on the problem of common randomness generation. So here in the common randomness generation framework, we have multiple parties who aim to agree on a common random variable with high probability. And here, this common random variable is modeled by the same output of the one-armed bandit. Now, the problem of common randomness generation was initially introduced by Alswede and Schieser in 1998 in this paper here. And in their work, they introduced several models for common randomness generation. And maybe the most standard model is the two-source model with one-way communication, where in their work they considered the case when the terminals communicate over rate-limited perfect channels, and the case when the terminals communicate over discrete memoryless channels. And they established a single-letter formula for the common randomness capacity for both models. Now, here we're going to present some applications of the common randomness generation. And we start with the first application, which corresponds to random coding over arbitrarily varying channels. So coding over arbitrarily varying channels can be seen as coding in the presence of a certain jammer. And when common randomness is available as a resource, this can prevent the denial of service attacks from the jammer. Now, one of the most obvious applications of common randomness generation is secret key generation, where under additional secrecy requirements, the generated random variables can be used as secret keys. Another application of common randomness generation is the modular coding scheme, where a common scenario in seeded modular coding is when the terminals or the legitimate parties have access to common randomness as an additional resource, and this common randomness can be used as a seed. Furthermore, here, common randomness, we can cite identification as a major application of common randomness, because common randomness as a resource can enhance the identification capacity of channels, and therefore an enormous performance gain can be achieved by taking advantage of this resource. And identification is more efficient than the classical channel message transmission scheme in many applications which require ultra-reliable low-latency communication exchange. For example, we have here as application 6G communication systems and car-to-car communication. Okay, now we're going to have an overview about our previous work. So in our previous works, we focused on common randomness generation from finite sources, from finite state-independent sources with one-way communication over several practical channels. And we start with the first channel. So basically, the first problem we considered was the common randomness generation over Gaussian channels with average power constraint, where we established a single-letter formula for the common randomness capacity for that model. Afterwards, we considered the problem of common randomness generation over slow fading channels with arbitrary state distribution, and we established a single letter formula for the outage common randomness capacity for that model. And after that, we considered a more general scenario in the sense that the terminals now communicate over an arbitrary point-to-point channel, and we derived general bounds on the epsilon uniform common randomness capacity, and we also derived general formula on the uniform common randomness capacity. So if you're interested in the results, here are the references here are the papers where we have these results. But in this work, we're going to focus on the problem of common randomness generation from compound sources. So basically, as far as we know, the problem of common randomness generation from compound sources was not investigated in the literature before. It was only investigated in the context of secret key generation, where additional secrecy requirements are imposed. However, in our work, we won't impose any secrecy requirements. So the compound source, in the compound source, we know that the source derives from a certain defined uncertainty set. So we know the set of states, but actually we don't know the actual state. And here, this uncertainty set remains unchanged during the observation timescale. So now we're going to introduce our system model for common randomness generation from finite compound sources with one-way communication. So here we have a compound discrete memoryless source with two components and with two generic variables. And here the set corresponds to the set of our states. So it is a finite set. And we assume that both terminals, so terminal A and terminal B, know the set, so know the set of states, and know the statistics. However, they don't know the actual state. And as you can see here, only the outputs at terminal B are state dependent. So this is the model we're considering. So here the compound discrete memoryless source emits independent and IID samples of the generic variable X, and also IID samples of the second generic variable at terminal B. And it is also assumed that terminal A can communicate with terminal B over some noiseless channels with limited capacity. So the channel is noiseless, but the capacity is limited. And here, if the capacity is 0, obviously no communication occurs over the channel. And it is here worth mentioning that no other resources are available to any of the terminals to generate common randomness. Okay, now a common randomness generation protocol consists first of a function phi that maps the outputs of X, so the generic variable X, into some random variable K, which is generated by terminal A. It consists second of a function f that maps the outputs of X into some message which is sent over the channel. And it consists third of a function psi here, which maps the outputs at terminal B and the message sent over the channel into some random variable L, index S. And here we have index S because it depends on the state. And here we should mention that the random variable K and the random variable LS take value in the same set, so they have the same alphabet. Now, such a protocol induces this pair, which is called permissible. And of course, here we should emphasize the fact that the distribution of the random variable K is independent, does not depend on the state. So that's why here we have no index here. Now, the question we're going to ask now is how much common randomness can we generate in one-way communication such that the error probability here is small for all possible states. So here, we want the error probability to be small for all possible states. And in order to answer this question, we're going to provide first the definition of an achievable compound common randomness rate and definition of the compound common randomness capacity. So how do we define an achievable compound common randomness rate? So this is a number, H here, so denoted by H here. So a number H is called an achievable compound common randomness rate. if for every choice of the constant alpha and delta, and here these are positive constants, and for sufficiently large channel use, or block length in this case, there exists a permissible pair of random variables. So here we have this pair k, which is generated by terminal, the random variable k generated by terminal A, and the random variable L index S generated by terminal B. And here the second random variable is state dependent, such that the following requirements are satisfied. So basically here, in the first requirement, we want the error probability to be small for all possible states. And here alpha is a positive constant that can be made arbitrarily small. And second, we want the number h to satisfy this inequality constraint. So this is the definition of an achievable compound common randomness rate. And now, how would we define the compound common randomness capacity in this case? Then we define the compound common randomness capacity as the maximum achievable compound common randomness rate. So this was the definition of a compound common randomness rate and the compound common randomness capacity. And now we move to the first main result of our work, which is a single letter formula characterizing the compound common randomness capacity, but this holds true only for the case where the terminals communicate over the channel. So this is the formula that we proved. So the compound common randomness capacity here is equal to this maximization problem. So this is the maximum over all auxiliary random variables U satisfying these two constraints of the mutual information between U and the generic variable X. And here U satisfies these two constraints. So we have the Markovity constraint here. So for all states, Ux, Y index S forms a Markov chain. And we have inequality constraint. So here, this difference of mutual information is upper bounded by the channel capacity. And basically, intuitively speaking, this difference of mutual information corresponds to the amount of information that terminal B does not know about the random variable generated by terminal A when its generic variable is observed. And this is exactly the amount of information that we want to send over the channel. That's why it should not exceed the channel capacity. And of course, here we have some constraints on the alphabet of each auxiliary random variable U. So the alphabet, so the set of the alphabet of the auxiliary random variable U is subject to this cardinality bound. So we have this bound on the cardinality, and this bound depends on the cardinality of the alphabet of the generic variable X, and it depends also on the number of states. So this was the formula for the compound common randomness capacity when the terminals communicate. And now we have some observations. So basically, as you can see, the compound common randomness capacity can never exceed the entropy of the generic variable at the terminal A, so entropy of X. However, if we choose the channel large enough, so if we choose the channel capacity large enough, greater than this term here, then the compound common randomness capacity reaches its maximum equal to entropy of X. However, if the channel capacity is small, if it is in this interval here, then we can find a lower bound for the compound common randomness capacity. So this lower bound is nothing but the channel capacity itself. And obviously, this bound is not tight. To see this, it's sufficient to consider the case when we have only one state and where the generic variables are equal. So in that case, the compound common randomness capacity will be equal to the entropy of X, which is obviously greater than the channel capacity, since by assumption, the channel capacity lies in this interval. Okay, now to have better insights about this result, so we'll provide a small proof sketch, and we will start by the direct proof, where we extend the common randomness generation scheme provided by Alsveda and Scheser to compound sources. And in their scheme, nearly uniform random variables are generated for every possible state, such that the following requirements are satisfied for every random variable U satisfying these two constraints. To prove this, we're going to provide some steps for the common randomness generation scheme. So how is common randomness generated? So we're going to start with fixing some state arbitrarily and considering arbitrary realization of our source outputs. And then we're going to consider some set of sequences, set of random sequences which are uniformly distributed on this set here. So this is the set of typical sequences with respect to some constant sigma of block length n and with respect to the distribution of the generic variable u. And we consider some realization of these sequences. Now, how is common randomness generated in this case? So at terminal A, we look for a sequence among these sequences which is jointly typical with the output sequence at terminal A. So once the sequence, so we look for that sequence, so denoted by U index ij. And once the sequence is found, then the first index of that sequence, which is denoted by I here, will be sent over the noiseless channel. Now, terminal B will decide for some sequence, which we denoted by U index ij tilde, if there exists some state S star such that U index ij tilde and the output sequence observed by terminal B are jointly typical, and here with respect to the joint distribution of U and Y index S star. And as you can see here, and so is common randomness generated. And as you can see here, we don't require any state estimation at terminal B for this common randomness generation scheme. Now we move to the converse proof. So what we want to prove is that this entropy rate here is upper bounded by this maximization term involving the channel capacity and some constant zeta depending on the block length and on the upper bound of the error probability. So this upper bound is alpha. And here this constant zeta, it tends to 0 when n tends to infinity and when alpha tends to 0. So to prove this, we need to find first a bound for this conditional entropy rate, and this conditional entropy rate depends on the state. So for every state S, we should bound this conditional entropy rate using some information theoretic tools like Infanus inequality. And the upper bound that we get is the channel capacity plus some constant zeta that vanishes as n goes to infinity and as alpha goes to 0. Now, the second step would be that we bound this entropy rate here. And to bound this entropy rate, we're going to define an auxiliary random variable u, which is defined as the concatenation of the random variable generated at terminal A and with the first j-1 symbols of the output sequence at terminal A, sorry. And also we have the concatenation with some random variable j, which is a uniform random variable on the set from 1 to n, and which is independent of our source outputs. And using information theoretic tools, we can prove this upper bound here. And to finish the converse proof, it's sufficient to show that the auxiliary random variable that we chose satisfies the constraints that we have in the maximization problem. So basically, it should satisfy this Markovitch constraint, and it should also satisfy this inequality constraint, where here we can make use of the results of step 1. And so we can prove the converse. As for the cardinality bound, so this is basically nothing but a direct application of the so-called support lemma, which is given here in this block. Now we move to the second main result of our work, which corresponds to deriving single-letter bounds on the compound common randomness capacity, but this time, this is for the case when the channel capacity is 0, which means that the terminals do not communicate over the channel. Well, we start with the lower bound, and here we're going to assume we have an additional assumption to prove our lower bound, which is that the probability distributions of all generic variables at terminal B are pairwise distinct. So here the distributions of all YSs here are pairwise different. And we have this lower bound for the case of non-communicating terminal. So this is our lower bound, which is equal here to the largest entropy of a common state-independent function of the generic variable at terminal A and the generic variable at terminal B. So this was the lower bound, and basically, again, here we can bound the cardinality of the alphabet of each auxiliary random variable U here, and we get this bound, which is equal to the minimum between the cardinality of the alphabet of the random variable of the generic variable at terminal A and the cardinality of the alphabet of the generic variable at terminal B. Now we move to the upper bound, and here we don't require any further assumption. So basically here, for the case of non-communicating terminals, the compound common randomness capacity is upper bounded by the minimum over all states of the largest entropy of a common, this time state-dependent function of the generic variable at terminal A and the generic variable at terminal B. And again, each auxiliary random variable here, we can found a cardinality bound on its alphabet, so we have the same bound as in the previous slide. Now, an important observation is that if there exists at least one state such that X and YS are indecomposable, have an indecomposable joint distribution, then in such a situation, for the specific state S, we cannot find a common function US because X and YS have an indecomposable joint distribution. And therefore, this implies that in that case, the compound common randomness capacity will be 0. Okay, now we're going to consider a second special case. So basically, we assume that the probability distributions are pairwise different. And we assume also that for every state, the generic random variable X can be fully determined by the generic variable at terminal B. And this should hold for every state. In that case, the compound common randomness capacity will be maximum, and it is equal to the entropy of the generic variable at terminal A. So this is a special case when we have maximal common randomness capacity. This is the best we can do. However, it is important to note that this assumption of distinct probability distributions of the generic variables at terminal B is only a sufficient but not a necessary condition. And to see this, we're going to provide this example of binary random variables. So we have here X, a binary random variable, a Bernoulli random variable with parameter P, and P here is between 0 and 1/2. And we're going to consider the case when we have two states, so state 1 and state 2. So for the first state, for state 1, we assume that the generic variables are equal. And for state 2, we assume that the generic variable at terminal B is equal to the complement of the generic variable at terminal A. And here, an interesting observation is that if we fix P equal, the parameter P equal to 1/2, in that case, Y1 and Y2, so the generic variables at terminal B will be equal. So the distribution of them will be equal. So if we fix P equal to 1/2, then the distribution of the two generic variables at terminal B will be equal. However, if we take P different from 1/2, then the distributions will be different. And in this example, we will see that the compound common randomness capacity for the case of non-communicating terminal will be equal to entropy of X. And this holds for both P different from 1/2 and P equal to 1/2. So here, with this example, we will emphasize the fact that the distinct probability distribution is only a sufficient condition. So how is common randomness generated for this example? We're going to fix some state. So here we have two states, either 1 or 2. And we're going to fix arbitrary realizations of our source outputs. And here, as you can see, it depends actually if the state S equal to 1, then the output sequences are equal. However, if the state equal to 2, then the output sequence at terminal B is equal to the bitwise complement of the output sequence at terminal A. Now, for the sake of common randomness generation perspective, we're going to consider the following mapping. So here we have some mapping with some subsets, where each subset here contains 2 sequences of length n. And here each sequence, so here we have some sequence and its complement contained in the same subset. So here 0, 0, and the sequence of all zeros and the sequence of all ones, for example, are contained in the first subset. And now, since we know that the source output or the output sequence at terminal B is either equal to the output sequence at terminal A or either equal to its bitwise complement, then we know that the 2 sequences, that the sequences at terminal A and terminal B are contained in the same subset here. And we're going to assign for each subset some index such that the random variable k will be equal to some index small k when its corresponding subset contains the output sequence here, the sequence. And at terminal B, we will set also the random variable and index s equal to some sequence k when the output sequence observed by terminal B is contained in the corresponding subset. And with this mapping, we make sure that the random variable k will be always equal to the random variable L index S. So here we generate common randomness. And for this example, the compound common randomness capacity is the maximum possible, equal to entropy of X for every P in this closed interval 0, 1/2. And it is important to note that achieving this capacity does not necessitate any communication between the terminals. And also, we don't require any state estimation with this map for this example. Okay, now to give better insights about this result, we're going to provide some proof sketch of the bounds, and we start with the lower bound. What we want to prove here is that the compound common randomness capacity is lower bounded by this maximization term, as we saw earlier in previous slides. And to prove this, we're going first to define some random variable u bar, whose entropy is equal to the desired lower bound here. And obviously, u bar satisfies the constraints here. And we're going to define consider some independent and identically distributed copies of that random variable that we will use them for the common randomness generation purpose. Now, how is common randomness generated? So terminal B will estimate the state, and this is done using the first square root n symbols of its observed sequence. And this is done as follows. So basically, it will decide on some state S tilde, such that if you take the first square root n symbols of the sequence, of the output sequence at terminal B, it should be element of this typical sequence, of this typical set with respect to the distribution of y index S tilde. So first it decides on some state S tilde such that this is satisfied. And now if such S tilde exists, then we know from advance that it is necessarily unique. Why is this the case? This is because we know that all these typical sets are disjoint for all states. And therefore, this is due to, and why are they disjoint? This is because we assumed that we have pairwise distinct probability distributions at terminal B. And it is here important to note that the probability of incorrect state estimation with this mapping vanishes as the block length tends to infinity. So here the error will be decreased, it tends to 0 as n goes to infinity. Now, once we estimate the state, we will use the remaining symbols for the common randomness generation purpose. And basically, both terminals will assign some predefined mappings to their observations. And So we have some predefined mappings, and we're going to assign them to get the random variables k at terminal A and L index S at terminal B. And here, if the state is estimated correctly, then we are sure that the two random variables are equal. And the probability here of incorrect state estimation is very low as n goes to infinity. Okay, now for the cardinality bound that we mentioned earlier, so it is basically, it follows immediately from the fact that all the generic variables at terminal B have the same alphabet, and the way we define, and the way U is defined, the auxiliary random variable, it is a common function of X and the generic variable at terminal B. And that's why we have here this upper bound on the cardinality of the alphabet of the random variable U. Okay, now we move to the proof sketch of the upper bound for the case of non-communicating terminals. So this is what we want to prove. And to prove this, basically it's sufficient to notice that the common randomness capacity for a compound system can be bounded by the minimum of the common randomness capacities for each state. So we have this, the compound common randomness capacity is the minimum over all states of the common randomness capacity for each single state. And to finish the proof, it's sufficient to establish a formula for the common randomness capacity for each single state for the case when the terminals do not communicate. And this formula was already pointed out by Asveda and Cheeser, and we have proved it also in our work. So it is equal to the largest entropy of a common function of the generic variable at terminal terminal A and the generic variable at terminal B. And so using these two results, we prove the upper bound. And again, here we have the same upper bound on the cardinality of the alphabet of each generic variable US. And we have the same upper bound, and the explanation is the same as in the previous slide, why we have this upper bound on the cardinality. Now, the last part is, in the last part, we're going to study some properties of the compound common randomness capacity, which are stated here. So we start with the first property, which states that the compound common randomness capacity is superadditive. So basically, if you take a system made up of independent components, then the compound common randomness capacity of the overall system is bounded below by the sum of the compound common randomness capacity of the individual systems. Now, another interesting property is the concavity here. So the compound common randomness capacity function is concave on this half open interval, which means that as the channel capacity increases, the rate at which the compound common randomness capacity increases slows down. And finally, the last property is continuity. So the compound common randomness capacity function is continuous on this open interval. And this means that any small changes in the channel capacity will imply small changes in the compound common randomness capacity. Okay, now let us summarize the most important results. So in our work, we studied the problem of common randomness generation from finite sources, from finite compound sources aided by one-way communication over noiseless channels. And we assumed that only the source outputs at terminal B are state dependent. So for this model, we established first a single letter formula for the compound common randomness capacity when the terminals communicate over the noiseless channel. So this is the case when the channel capacity is positive. We also established single letter bounds on the compound common randomness capacity when no communication occurs over the channel. So this is the case when the channel capacity equal to 0. We also provided a common randomness generation scheme for a two-state binary source. And in this coding scheme, no communication over the channel occurs, and we achieve entropy of X. And here the common randomness state that we achieve is entropy of X. And here we're going to present some open problem in this direction. So the first open problem would be is to completely characterize the compound common randomness capacity in the absence of communication, because so far we have only bounds. And it would be interesting also to extend the model such that, both source outputs at terminal A and terminal B are state dependent. So this brings us to the end of the presentation. Thank you for your attention.
Okay, thank you, Rami, for that talk. Are there questions or comments?
Thanks for the nice presentation. Did you say what decomposable or indecomposable is, at least when you mentioned it as a criterion for the common randomness capacity without communication to be larger than 0 or 0? When you mentioned it there, I didn't remember what it was. So what is it?
Yeah, so, sorry, probably I forgot to mention it. So there's here, I mean.
Because I think it's quite like to get an intuition for the result. I think it's quite important for me to understand when is it 0, or it's surprising when it's larger than 0 to me.
So here, if it is indecomposable, you cannot find such common function between the common function here. So here, if x and ys have a decomposable distribution, such common function won't exist. There's no random variable us such that you have.
So that's the definition of composable.
Yeah, but it is more technical. I forgot to mention it, but yeah, it is provided in Witzenhausen paper. If you're interested, then you can have a look at it.
Okay, yeah. And one about the how you write the theorems.
Yeah.
So in this maximization, and then you maximize over use such that for all S certain criteria are satisfied. Is this the same as maximizing over all use and then minimizing over all states such that the criteria are satisfied?
No, that should be not the same. So I'm not sure if this is the same.
Because like for me, it's about comparing it, for example, also to the upper bound where you have the min max, and in the lower bounds or in the capacity that you showed before, it seems to me that it's something like a max min. So to get
but you cannot like interchange them here, so we don't get the
because the state set is not convex probably, but
probably in particular cases you can interchange them, but here.
But so is this main theorem like, or the lower bounds sort of max min then, or what?
You mean here?
Yes. Can you write this as a max min or what?
Yes. So
somehow.
Yeah, I need to think about it, how to write in terms of max min. I didn't think about it in this direction, but yeah. Probably you can discuss this if it's possible.
Okay, yeah, because I think to get a feeling about when things are equal, I think this is interesting.
Yeah, thanks for the reminder.
Thank you for your presentation. I had actually a similar question on this quantity.
Yeah.
So are you able to compute this distribution using some typicality, or is this too strongly dependent on the states?
You mean in which context?
Here, for example. Like usually, well, you can probably use typical sets to compute.
This could be a good direction for future research, but so far we have only the formula, but it would be good if we can find, you mean so you're looking for this U, how we can compute this U that maximize this problem, right? Yeah. But we didn't think about this in this work.
Because I think, I'm not sure if I remember it correctly, but to maximize the entropy, there are some tools also from statistical mechanics. But I'm not sure in how, also related to his question, how the states S then complicate the situation, but maybe this is something that could help.
Yeah, so maybe this, you can think about it, how to find such maximizing view. So complete
I thought because you used typicality also later, so maybe you used it also here.
So no, we used it only for proving the achievability part, but not for the finding the optimal U here.
Okay.
But probably you should have to look at this.
Yeah, thank you.
So Rami, of course, you should remember that. So we are in the case of R equal to 0.
Yes.
Yeah. And, in this case, of course, it has a combinatorial and a probabilistic flavor. That's So that's why I guess typicality is too weak, because so an equivalent condition to saying that you have this partition is just you have to understand the zero pattern, you know, where your correlation, so where the probability of x equal to this and y equal to this is equal to 0. That's very important, and I guess that for this, you know, typicality is too optimistic as a condition. So it makes a difference if this is 0 or greater than 0. That's the combinatorial part of this. So that's why I think Johannes, as he mentioned, this is a very surprising result because it depends on the combinatorial properties of the joint distribution.
To me, your achievability seemed to suggest somehow, so like this, basically, can you go back to this, to the achievability? Because if I remember correctly, you have somehow something,
to 0 or?
The typicality proof of the achievability there. Yeah, for r greater than 0.
Yeah.
So do I understand correctly? You select this uij at the center to be jointly typical with x, and you select uij bar or so at the, or from uij bar at the receiver, you select y such.
No, y is the source output.
Yeah, y is.
So this is what the terminal B observes, and we look for a sequence uij tilde. So terminal B will decide for the sequence if there exists some state, and state S star, such that that sequence and its observed sequence are jointly typical with respect to the joint distribution of U and YS star.
Okay, and where is the influence of the channel input or of the channel output? Because it seems you select just something that's jointly typical with your source output.
So here,
but without...
the channel we send only the index.
Ah, okay.
It's a perfect channel.
Okay.
And here the influence, so you're showing, so you look for the same code book, you look for a sequence which
I was
satisfies.
looking for the noisy channel. So. Thanks.
Okay, then thank you again.